Hello, and welcome to a lecture on pyramidal and sectoral horns. I'm Steve Ellingson. First, a prologue, just to remind you of where we're coming from. Before attempting this lecture, please make sure you've viewed the lecture on the H-plane sectoral horn, because I'm going to assume that you already know about a few things, and those include the following. First, generally, the horn concept, what it is to be a horn antenna. Also, I've talked about the H-plane sectoral horn, the concept, the analysis of these types of horns, and the design of these horns. Also, in that previous lecture, I talk about different methods of analysis and how they apply to horns generally. Basically, there's three types of methods that we can imagine using: aperture theory, empirical methods, and full wave methods. At the end of this lecture, I'm going to invoke the idea of one additional method of analysis, and that's diffraction theory, that is UTD, for example. Now an overview of this lecture. First, I'll introduce the pyramidal horn, the concept, results for the aperture field, the radiated field, and the pattern. And that's as far as we're going to go with the pyramidal horn for a moment. Then I'll switch to a special case of the pyramidal horn, known as the E-plane sectoral horn, which I'll abbreviate EPSH. Now, as you can imagine, there is a connection between the E-plane sectoral horn and the H-plane sectoral horn, and we'll address that. It turns out that they're both special cases of the pyramidal horn. For the E-plane sectoral horn, it's relatively easy to come up with some expressions for directivity and design equations, so we'll do that. Once we have results for the E-plane sectoral horn and the H-plane sectoral horn, then it's somewhat easier to come up with relevant design information for the pyramidal horn. So we'll return to that antenna. We'll discuss design strategy and directivity. And then finally, concluding remarks. So here's a picture of a pyramidal horn. In this case, the dimensions, which are indicated here, are for X-band operation. X-band is about 10 gigahertz, plus or minus a few gigahertz maybe. So as you can tell, a pyramidal horn is so named because it has roughly the shape of a pyramid, where the vertex of the pyramid, the tip of the pyramid, would correspond to a point in the waveguide. Also, I should note here, just so there's no confusion, this picture is from another textbook. And in that textbook, the variables are somewhat different. So A and B here are different from the variables I've been using for A and B. So sorry about that, but it won't be relevant because we don't need this slide in the rest of this lecture. Okay, the pyramidal horn, now using variables that we're used to. First, we can look at in the H-plane of a sectoral horn. And it's very similar to an H-plane sectoral horn. In fact, it's identical in this particular plane. So in the XZ plane, as I've assigned the coordinate system here, the opening has dimension A. There is this dimension R1, which goes from the aperture back to a point in the waveguide. There is a dimension little a, which is the width of the waveguide in this plane. And then all the other variables that you... In the E plane, we also have a flare. So this is a new thing. This is the same description that we had for the H-plane sectoral horn, but to make it a pyramidal horn, we also flare now in the E-plane. In the E-plane, we'll have an opening dimension of B, big B, and the waveguide has dimension little b, just to keep the notation consistent. And then just as we had a dimension R1 in the H-plane, we'll have a dimension R2 in the E-plane. And then all the other variables follow suit. L sub h becomes L sub e, alpha sub h becomes alpha sub e, and so on. Just as in the case of the H-plane sectoral horn, we will feed it with a square waveguide having a TE01 mode. And the excitation will be aligned as shown here. As you may infer, the electric field lies in the E-plane. So this is the E-plane because this is the plane in which the electric field vector lies. So if I were to draw the same vector over here, it would look like this, the arrow pointing out of the page. And as before, this is the expression for the incident field in this case. It's y-hat polarized, some complex value related to the magnitude and phase of the source, and then this cosine pi x over a relationship. So first we want the aperture field. This is the expression I just wrote down for the TE01 mode in the waveguide. An educated guess for the aperture field, that is the field at z equals 0, as I've defined the coordinate system here, is simply to extrapolate from the throat into the aperture. This is precisely the same thing we did for the H-plane sectoral horn, except now we're doing it in both the E and the H-plane, since they both flare. You'll note this expression here is required due to boundary conditions. The tangential component of the electric field must be 0 on the E-plane walls of the horn to satisfy boundary conditions. So we get no x-hat component at the walls. Also, as before, we'll re-reference the phase distribution to the center of the aperture. So that entails simply replacing this distance with this distance, and this distance with this distance. All right, subtracting off r sub 1 or r sub 2 in each case. Now, as before, we use type 1 equivalence. The electric field is a sum of the electric fields in the aperture associated with equivalent electric currents, E sub A, plus the electric field in the aperture associated with equivalent magnetic currents, E sub F. We can write those expressions down just as we did before. Here's the expression for E sub A, where again Q sub X and Q sub Y are the associated components of the spatial Fourier transform. Here is the associated expression for the electric field associated with magnetic currents, and here are the components of the associated spatial Fourier transform. And then just to write these down explicitly, here's how we can get those spatial Fourier transforms. Here's the P transform, here's the Q transform, and this is all old news at this point. In fact, not only is it old news, but it's exactly the same as what we did for the H-plane sectoral horn. To get the radiated field, we have to evaluate these things. So here's P sub Y. Here I'm just substituting now the expression that we previously obtained for the aperture field. So it's looking a little bit ugly, but we'll try to clean this up as we go along. In any case, it entails an integration over the aperture, which is x equals minus a over 2 to x equals plus a over 2, and y equals minus b over 2 to plus b over 2. These pieces are different from what we had in the case of the H-plane sectoral horn, and they're associated with the fact that we are now flared in the E-plane as well as in the H-plane. We can factor these integrals, so we have one integral over x, one integral over y. So the two brackets are two separate integrals which factor readily into those two separate variables. And just as we did with the H-plane sectoral horn, we will throw up our hands and say we can't do this in closed form. At least I'm not aware that we can. So I will give this integral a name and then recognize that I'll have to do it numerically when the time comes. And I'll call this I sub p, which is a function of theta and phi. So for each value of theta and phi that we want to evaluate this for, we will have to do that numerical integration over the x dimension. And then we have a second integral that we will have to do. This is different from the case with the H-plane sectoral horn, because now the aperture fields are varying in both dimensions. So this is the associated integral that we will have to do over the y dimension, and we'll give it the same name, except we'll introduce the squiggle up here to indicate that it's a different integral, the one associated with the E-plane. So we can now compactly write the expression for the associated Fourier transform as E sub naught times the product of these two numerical integrations. For Q, we can do the same thing, except now we have to integrate over magnetic field intensities in the aperture. Again, as in the H-plane sectoral horn, we have to be a little bit careful about how we do this. The approach that we'll use here is to assume the plane wave relationship in the aperture. This is the plane wave relationship right here. and we want the x component, so we dot this into x. We can simply take the x component of the cross product here, that's what this is, and then that's over eta, which is the wave impedance in whatever medium we're in, typically free space. But then we have a bit of ambiguity, as I've indicated here, and that's what is, or where is, the tail of the pointing vector. Is it in the aperture or is it in the throat? This is a little bit ambiguous. So to avoid this hassle, we'll simply say, or we'll simply invoke the transverse electromagnetic assumption. And in that case, the whole expression just simplifies to this, minus the y component of the electric field in the aperture divided by the wave impedance. So now we can compactly write the desired component of the Fourier transform as, once again, the product of these two integrals with a different coefficient out front. Taking stock, the total electric field that's radiated is the sum of these two components. Here are expressions for the two components. When I substitute what we've got now, these factors q sub x and p sub y that we just worked out, here's what we get. Here's e sub a, again, simple substitution into the expression we just wrote up here. Here's e sub f, again, simple substitution. And now we add them up, and this is the desired result. So the total radiated field plus jk, k is always his wave number, 2 pi over lambda, e naught, a spherical wave because we're in the far field. Remember, these are far field expressions. The product of the two numerical integrations, 1 over x and 1 over y in the aperture, an obliquity factor, which we should not be surprised to see, and then a polarization vector. So despite having some relatively ugly math to start off with, this really is not so bad if we organize the factors in a way that allows us to recognize what the contributions are. Pattern. We're interested in a normalized pattern, so we can throw away all the factors which do not change as a function of pattern variables, theta and phi. The H-plane is phi equals 0, so the associated electric field is y-hat polarized, the product again of these two numerical integrations, and then an obliquity factor. The E-plane is phi equals pi over 2. That's proportional to theta hat, the product of these two numerical integrations, and another obliquity factor. Now we can just go ahead and plot this. This is an example from your book, Stutzman and Thiel, the 2013 version, 3rd edition. This is example 9-7. So example 9-7, I think they specify a frequency and then physical dimensions in millimeters or centimeters. I will simply keep this frequency independent, and I'll give the dimensions in wavelengths. So R1 is about 10 wavelengths, A is about 5.5 wavelengths, R2 is about 9.3 wavelengths, and B is about 4.3 wavelengths. When we evaluate the pattern of this particular pyramidal horn, this is what we get. The solid line is H, the H-plane. Just be clear, that's the H-plane. And this is the E-plane. And what we get is kind of interesting. The H-plane is not surprising. It shows some directivity. The E-plane shows some ripple. It's from a diffraction from the edges of the aperture. Now, you should note right away one utility of the pyramidal horn, and that's that we can have patterns which are approximately balanced. That is, we can have E and H-plane patterns which may not be identical, but they're similar. You'll remember the H-plane sectoral horn does not have this property. The beam width in one dimension is much, much greater than the beam width in the other orthogonal dimension. For pyramidal horn, we can arrange to have the beam width very similar in the two planes, and the pattern also be similar in those two planes. Okay, so now I'd like to talk about two special cases of the pyramidal horn. One you already know about, the H-plane sectoral horn. The other one that we're about to talk about, the E-plane sectoral horn. The E-plane sectoral horn is a horn which is flared only in the E-plane, just as the H-plane sectoral horn was one that was flared only in the H-plane. And that's the only difference. We have everything we need to analyze an E-plane sectoral horn. First, let me remind you of what an H-plane sectoral horn looks like. I can use the exact same math I just developed for the pyramidal horn, and I can let R2 be ridiculously large. In this case, I'm simply making it 1,000 times B, simply to give me a value which is very, very close to an ideal H-plane sectoral horn, and which allows me to use the pyramidal horn equations. So when I do this, I get the result that you hopefully recognize from the previous lecture. Here is the H-plane. Here is the E-plane. It's as we expect. In fact, the only difference from the example I did in the previous lecture is a small change in the E-plane out here. And we shouldn't be too worried about that. It comes from the various approximations associated with the pyramidal horn, and perhaps a little bit from this assumption. But we're really not too concerned about it. And the reason is because we wouldn't expect that any of these results would be very good this far away from broadside. Remember, the aperture integration equations that we're using are not expected to be very good at angles which are far from broadside to the aperture. So we're not too concerned about this difference. The important thing is around here, the results agree very, very closely, which validates our pyramidal horn expressions. For the E-plane sectoral horn, again, here are the variables we're going to use. We simply use the E-plane pyramidal horn variables. That's what we have up here. In the H-plane, we simply extend the waveguide without flaring it out. We apply TE01 mode exactly the same way as we did before. Here's the expression. It's the same expression for the excitation. And so we have everything we need to calculate a pattern. We simply use the pyramidal horn expressions. And in this case, we'll let R1 be very, very large compared to A. That makes this a very, very close approximation to an ideal E-plane sectoral horn. And in this case, we're choosing A to be 1 wavelength, R2 to be 6 wavelengths, B to be 3.5 wavelengths. Again, to make this the complement to the H-plane sectoral horn that we've already studied. So here's what we have. This is the H-plane. This is the E-plane. This is junk. That shouldn't be there. So what we see is hopefully what you have come to expect, that the E-plane is flared out, so its half-power beam width, which is right here, is relatively narrow compared to the half-power beam width in the H-plane, which is not flared out. This is what you'd expect. And now you should also come to expect that the E-plane has these ripples in it. Again, that's diffraction. And now just for comparison, I will show you the H-plane sectoral horn result just to allow you to see very quickly how they compare. This is the E-plane for the H-plane sectoral horn. This is the H-plane for the H-plane sectoral horn. And again, H-plane's narrow, E-plane's relatively wide. You get the result that you expect associated with which dimension has been flared out. We can compute the directivity of an E-plane sectoral horn. We can do this in the exact same way that we did it for the H-plane sectoral horn. You will recall I used this particular expression, which we have derived many lectures back. And I can show you directivity, this is in linear units, as a function of B, which is the flare in the E-plane. I'll use A equals 1 wavelength, and then I can show 3 different curves. For example, the solid curve is R1 equals 6 wavelengths, R1 equals 10 wavelengths, this is 10 lambda, and then R1 equals 15 lambda here. And as you expect, as I make R1 bigger and bigger, I can make the overall directivity higher and higher, but I have to choose the correct optimal value of B in order to do that. So there is always an optimal choice of B for any given length R1. And this is exactly what we saw for the H-plane sectoral horn. And for the same reason, there is an optimal value because on this side, the aperture is smaller than what we can accommodate. On this side, the phase cancellation in the aperture starts to diminish the directivity. And just to remind you, this was the H-plane sectoral horn result. Okay, so useful design equations for H-plane sectoral horns and E-plane sectoral horns. We already worked it out for the H-plane sectoral horn, and I'd just like to repeat it for that type of horn here, just to put everything in the same framework. First, note that the following equations are obtained by curve fitting to the results that I've already shown you. Then we compute an aperture for optimal directivity. For the H-plane sectoral horn, it turned out that the optimum aperture, A opt, was the square root of 3 lambda R1. If we want to achieve maximum directivity, then we choose the maximum allowable axial length, and then we compute the optimal aperture. That's the way it goes. For the E-plane sectoral horn, we can have a similar expression. It's B sub opt is the square root of 2 times lambda times R2. Very similar looking expression, again obtained by empirical methods. The half-power beam width in the appropriate plane, it's useful to know expressions for that in case this is the thing that you're concerned about. For the H-plane sectoral horn, it was 78 degrees times wavelength divided by A sub opt. For the E-plane sectoral horn, the only difference is 54 degrees, and we're dividing by B sub opt. Directivity, hard to estimate accurately, once again, better to compute directly and not very difficult. Directivity is usually not a problem calculation-wise because we need to do the integrals only once. Patterns, on the other hand, are kind of a pain in the neck because we have to repeat the aperture integration over and over again for every pattern point. For those reasons, it's better just to compute the directivity directly, and it's really not a hassle to do that. And then, once again, gain is about the same as directivity as long as the waveguide portion of the horn is properly designed. You don't have excessive losses there. There's no big impedance mismatch or something like that. In the previous lecture, I demonstrated the accuracy of the H-plane sectoral horn equations. I could do the same thing for the E-plane sectoral horn equations. Here are the results. I won't go through these in detail, but they're here simply to demonstrate that these all work out. So here, as I did before, are results which are computed and then determined from design equations. Computed from the design equations and so on. And you can see that the agreement is very, very good. So now we return to pyramidal horns. Specifically, how do we design pyramidal horns? For the purposes of estimating directivity and half-power beam width, a pyramidal horn is factorable into an H-plane sectoral horn and an E-plane sectoral horn. In fact, we've already seen this, that these two types of horns are special cases of the pyramidal horn, and so it kind of makes sense that a pyramidal horn is in some sense the product of those two types of antennas. The directivity of a pyramidal horn can be estimated through this expression. So this is one of the directivity equations that we have probably discussed long ago. For any square aperture, which is what the pyramidal horn gives us, we can compute the directivity in one dimension and directivity in the other dimension, and then we can tie this all together using expressions which are normalized to wavelength, and then this factor pi over 32 in front of it. This is not a horn equation. This is just a general expression for the directivity of an aperture. You should not infer from this that optimizing the H-plane and E-plane of a pyramidal horn separately optimizes the gain of the pyramidal horn overall. Simply because you can obtain a good estimate of the directivity by looking at the E-plane and the H-plane sectoral horn performance separately does not mean that you can optimize the performance in this way. You have to use another approach. The approach goes like this. First, there is a fact which is borne out by an analysis of lots of different kinds of horns and measurements, and the fact goes like this. The best possible aperture efficiency from a pyramidal horn is typically found to be about 51%. Remember, aperture efficiency is the ratio of effective aperture that you achieve to the effective aperture of an ideally illuminated aperture. So for this, it is about 51% for pyramidal horns. No matter what you do, it's hard to achieve an aperture efficiency greater than this. Now this is useful because we also know that we can relate aperture efficiency to gain. Now this would be the effective aperture of an ideal aperture. So what we should actually expect for the best possible designed horn, pyramidal horn, would be that the actual gain should be less than by this factor, 0.51. So the idea here is that we have a relationship between the ideal effective aperture and the best possible effective aperture that we can hope to achieve for a pyramidal horn. And now we can use this as part of our design process. As we say here, useful for determining optimal A given an optimal B and vice versa. So the trick will be get either A or B, and then we can get the other one through this expression. So here is the procedure. Previous slide was just setting this up. The usual problem that we have is that the gain of the horn and the waveguide dimensions are specified, and someone would like to design a horn with the shortest possible axial length. Now for this we have an empirical expression. It's a fourth power polynomial in the dimension of the large aperture, big A. So you see here, big A to the fourth, big A cubed, and then big A, and then other factors related to the waveguide dimensions, the gain that we achieve. Now this is an ugly looking expression. We would like to solve it for big A. It's easily done numerically. You can use an initial guess of 0.45 times lambda times the square root of gain. That'll get you close, and then you can iterate a little bit to find the solution to this equation, which gives you the value of A that you're going to use as A sub opt. Given that value of A sub opt, which you get from the previous step, now you can solve for B sub opt. Now, a bunch of approximations have gone into this, so you check to see if your design is reasonable. You check the directivity equations, you see what kind of directivity you're getting out of this, and then once you're happy, or once you think this is working out, then you proceed to a full wave simulation and make sure everything's working. The usual question I get is, why not just iterate the full wave solution? That's for two reasons. One is, perhaps there's a computational issue here in that maybe the solution isn't well conditioned, or that maybe just takes too long. In either case, this usually is slow compared to this kind of process. So it's very common to iterate through this kind of process and then check using the full wave solver, as opposed to simply iterating the full wave solver. But it's not out of the question just to do the latter. This, I would argue, gives you a little bit more insight into how to adjust the performance of the horn given a existing horn design and then trying to modify it somehow. Simply following this procedure, you have no clue how to change A and B to optimize or to push the design in some direction. So let me return to the pyramidal horn design that we previously looked at, also the one in your book. This is the result I showed you a few slides back for the normalized pattern. I can compute the directivity of this pattern. Directivity using aperture integration, I get 21.8 dB. I can also compute the directivity using this assumption. Right? If this has been an optimally designed horn, then this expression should give me the same directivity. And look at this, it's the same to within 1/10 of a dB. Then I can also use this expression for the directivity. That approach gives me 22.2 dB. So very slightly higher, half a dB or so, but certainly within the ballpark. All three of these results agree, so we have some confidence in our directivity expression. And it appears that this horn is therefore close to being an optimal design. Now, a good exercise for you is to see if you could do this as a design problem. In other words, given little a, little b, length R1, for example, can you develop the remaining expressions and then repeat these directivities? I highly recommend that you do that to confirm your understanding of these concepts. Concluding remarks. First, I have not told you why we like to use pyramidal horns, or I may have mentioned it very briefly. The big reason would probably be closer to balanced patterns. That is, the E plane and the H plane are closer to being the same. And this is typically a feature that we want in a lot of applications, including dish design. Another question you might ask is why use an H-plane sectoral horn versus an E-plane sectoral horn? That is, when to use one or the other. And this is really a trade-off that depends on a lot of things. They have different half-power beam width characteristics. They have different uniformity of pattern. And by that I also mean ripple, right? The E-plane sectoral horn has some ripple in it. The H-plane sectoral horn really doesn't. And there's a directivity trade-off. So these three things really kind of drive the choice between the two. You really have to look at the requirements of the application to determine which combination of these three things is right for you, and then that will determine whether you should use an E-plane sectoral horn or an H-plane sectoral horn. Now, as promised, I want to point out another way to analyze these types of horns, and that's UTD, the Uniform Geometrical Theory of Diffraction. Very tempting to do this. The reason is you saw a few slides back that the E-plane sectoral horn showed clear signs of diffraction, that ripple in the pattern. And it is very possible to analyze horns very accurately using UTD. But I have to warn you about one thing, and that's slope diffraction. Slope diffraction refers to the fact that UTD, left to itself, predicts zero diffraction when there's zero incident field on an edge. And in a horn, you have the situation that the edge illumination might be zero because of the boundary condition, E tan equals zero. Now that doesn't mean you don't have diffraction, it just means that UTD doesn't do it right. There's a simple correction to UTD diffraction coefficients. It's straightforward to implement, and you can look this up if you'd like to take this approach. Not very complicated, commonly done, so you should consider that if you have an application for this. Now, where do we go from here? We've talked about pyramidal horns and the special cases of H-plane sectoral horns and E-plane sectoral horns. What would go next? Circular horns. So circular horns, as you might expect, are horns which are based on circular waveguides, and the circular waveguides are then flared out radially. Why might we want circular horns as opposed to E-plane or H-plane sectoral horns or pyramidal horns? Commonly, it comes down to this issue, the balanced nature of the pattern. It turns out that we can also do some other clever things with circular horns that give us some desirable trade-offs. So that's the topic for another lecture. This concludes this lecture on pyramidal and sectoral horns.